All right, so now we're ready to look at logistic regression when we have more than one predictor in the model. So in multiple linear regression, remember we went from having one predictor to multiple. We did simple linear, kind of reviewed it, and then did multiple, and now we go from having a single predictor in logistic regression to having multiple predictors. And we still have two forms in our model, the logit form and the probability form. And we can have transformations of predictors, we can have interactions, and we can have either quantitative or categorical predictors. So in this first example, we're trying to predict the probability of a subject being gay based on this dilate difference variable, the difference in pupil dilation. And I gave you a bunch of code here. So this is where we're using that third method from the previous, from the Part 5 document, where we're breaking the cases into groups so that we can get some points to plot in our logit plot. So if you just take some time to kind of look at the code and notice, for example, what this cases is doing is basically with the tally command is just adding up how many values are in group 1, and then the mean here is rounding, as it says, to 3 decimal places. The dilation difference value for the whole group, it's finding the average for the group, finding the minimum, the maximum. Okay, this gay one is adding up all the ones to tell you how many predicted gays are in that group. And then here's where it's doing the adjustment that I mentioned in the Part 5 video, where we're adding 0.5 to the numerator and 1 to the denominator because our group sizes are kind of on the small side here. And so that's why this last column is, so we have the adjusted proportion from making that adjustment, and then the logit, the log odds there. Okay, so what we want to do then is create a plot where we look at, let me just do this in another color. Our plot is going to have the mean on the x-axis and the logit of the adjusted proportion, log odds, on the y-axis. Okay, and that's what we're trying to see, is whether that's roughly linear, and we can see that it is. And notice I'm using here just a plain linear model instead of a GLM, because now I've got it down to 2 quantitative variables basically, and I want to see if there's a linear relationship between them, and it appears to be so. So then another part of our exploration is to see if there might be a difference in the log odds of being gay for females versus males based on that dilate difference. So again, we have a pretty big table down here, but in the code, basically it's doing 2 columns at once. So for example, this is giving you female cases and male cases. That's columns 3 and 4. And then 5 and 6 are giving you the female mean, that's the dilation mean, and the male mean, the dilation difference mean. And then this next 2 columns is giving you the female count, how many females in the group, and the male count, how many males in the group, etc. Okay, and again, it's using the adjustment. The group sizes are kind of on the small side. And then the last thing is giving the log odds for that adjusted probability or proportion. Okay, so based on that, we can create the plot here. So I don't have a legend, but the males are in blue and the females are in purple. And so what we see here by looking at this plot is that the male and female lines are not exactly parallel, but they're close to being parallel. They maybe are not so much different from parallel that we might think there's an actual interaction there. But notice that we can add this sex male predictor because we think anyway that their intercepts seem different. So note that if sex male is 1 versus 0, we have the same slope beta 1, but we'll get a different intercept, either beta 0 or beta 0 plus beta 2. Okay, so then we can create a model that has both dilate difference and the sex predictor in it. And we're going to come back to the deviances in another video, but the model equation is at the top of page 6 here. And again, we can convert that to probability form. So these estimated coefficients are based on the model summary output, and we've created here probability and logit version. So again, we've got the log linear based on the model. The two lines are parallel, and then we have the probability version where we get logistic curves. Okay, so we can use the model to make a prediction, and I sort of have what I put in quotes by hand sort of brute force method first, but also there's a predict function in R that we can use. So FYI, if you're using the predict function, then when you put in this first set of code, let me just find, where I have this in my notes. You should get about a 1.67-ish for this, and then here you should get about a 0.84. And then we can do also for a female that has a dilation difference of a half. Again, FYI, if you run this code, this should be about a 0.38. And this should get you about a 0.59. That's e to the 0.38. So just as a reminder, this is e to the 1.67. over 1 plus e to the 1.67. So it's odds over 1 plus odds gets you the probability. And similarly for the 0.59, it's e to the 0.38 over 1 plus e to the 0.38 is where that comes from. So to get from odds to probability, we do odds over 1 plus odds. And because what's coming out of the model in the logit form is log odds, we have to exponentiate to get from log odds to odds. And then how we can sort of interpret coefficients. So I use the dilate difference value of 3.29 here. And basically, so it says if we increase the dilate difference value by 1 unit, which we were not told what the units were on that. I could make a guess, but we weren't officially told. But anyway, if we have a 1 unit increase in the dilate difference, then we're going to multiply our odds of being gay by a factor of about 27, which is big. And if you notice on this logistic curve here, if we increase our dilate difference by 1, then our amount of increase in the probability of being gay is pretty large. It's basically half of what it could be. And then let's see, so if we put in a 1 for sex male and a 0 for dilate difference, that's where this negative 1.27 plus 1.29 times 1 for being male, we get a 0.02. And that's again a dilate difference value of 0, so the 3.29 times dilate difference is gone. And so we get a log odds value of 0.02, so the odds are e to the 0.02 or 1.02. And again, if we take odds over 1 plus odds, that gets us a probability of 0.505. And if we go back up to our logistic curve, again, if we're at a dilate difference value of 0 and we go up to the curve, that's roughly a probability close to 0.5, so that makes sense. And then if we look at a dilation difference of 1, now we have e to the negative 1.27 plus 3.29 plus 1.29. We're talking about a male. And that gets us an odds value of 27-ish, which is a probability of almost 1. It's a very high probability, and again, we could estimate that here. If our dilation difference value was 1, then our probability of being gay is practically 1 based on the logistic curve, and again, that's for a male. So just keep in mind, when we're focused on one of our predictors like dilate difference as we were here, then we should be comparing man to man or woman to woman. So we imagine that other predictors are staying constant, or the best thing we could say is allowing for simultaneous changes in the other predictors. Here's what we expect to happen when, in this case, dilate difference increases by 1. All right, and then for our second example, we go back to the medical school data, and we're comparing now two models, one that has just MCAT and one that has MCAT and GPA. So we kind of started with this question way back when of, is it better to increase your GPA or your MCAT, or how can we compare having both in the model? So what we see here is with just MCAT in the model, we have a significant p-value on that slope coefficient, and we see our deviance values there. If we add GPA, we see that GPA is definitely got a low p-value, but notice that the MCAT does not. It's got kind of a high p-value. But here's a case where, again, you want to look at that drop-in deviance test, which we haven't gone over for a case of comparing a 2-predictor model to a 1-predictor model, but I wrote in here that the drop-in deviance test does give a low p-value, so from that we would conclude that GPA is useful as a second predictor. So once you already have MCAT in the model and you add GPA, you notice that the coefficient for the MCAT went way down, but that's partly that's basically because GPA is now doing some of the predicting, and so MCAT is not sort of doing as much. And GPA and MCAT, as you might imagine, have a medium strength correlation between them. And also just mentions that the coefficients for GPA is quite a bit bigger compared to the coefficients on MCAT, but that has really to do with the scale. All right, and then what if, so once we have GPA and MCAT score in there, what if we want to also add how many applications the student put into different medical schools? So in this case, again, we can look at the p-values for the individual predictors. It's going to be more useful for us to look at the drop-in deviance test, which we will do in the next video. But here, the drop-in deviance test gives a p-value of 0.56, which is kind of close to the p-value for the APS coefficient. And so it's once you already have GPA and MCAT in your model, adding APS is not really giving you much additional predictive power, so it's not worth it to leave that variable in there.